Okay, welcome to the fourth lecture this week. Last lecture we were we finished at a point where we said, look, in order to make, we talked about community noise levels, traffic noise index, L equivalent. All of these require measurement of the sound levels, and the measurement is done through a microphone. I told you that condenser microphones are the preferred choice for high fidelity microphones. Then there are basically three types of microphones that are sold by the microphone manufacturers. Free field microphone, which is used for a wide variety of applications. Then there are special microphones called pressure microphone and a random incidence microphone. Okay, typical spec sheet from a manufacturer we will look at. This is from Gras, Gunnar Rasmussen Sound and Vibration Company, Denmark. So you can see that he has, of course, a nomenclature 40AF, 40AC, 40BE. These are product catalog numbers. So you can call off and say, I want a 40AF microphone. The sensitivity basically, which is millivolts per Pascal. So if I have 1 PA pressure acting on the diaphragm, how much voltage change does it produce? You can see that it's not much. In fact, the 40BE just produces 4 millivolts output, whereas the 40AF produces about 50 millivolts. Now, frequency range. This is the range where the sensitivity is flat. That means for the 40AF microphone, that would mean from 3.15 Hertz to 20 kilohertz. Essentially, the sensitivity is flat. Now, outside of these things, the sensitivity will not be the same. Also, so you can see that the 40AC actually has an upper limit. It can go up to 40K. Whereas the 40B, which has the lowest sensitivity, starts only from 10 and can go all the way up to 100K. Now we will see why this is the case. Why do I have different sensitivity ranges? We will see soon. Now the dynamic range is what is the lowest amplitude I can measure. So although threshold of human hearing is 0 dB, the microphone itself, the diaphragm itself, because of its sensitivity, there is a threshold below which it will not be able to measure. So the lower limit basically is dictated by that. So if the amplitude of pressure fluctuations is below 15 dB, you cannot trust the reading that is coming from this microphone. So the sound pressure level will have to be more than 15 dB for this microphone to pick up. So you can see that both of these are with polarization 200. So you can see that they are the standard condenser microphone with a polarization voltage, and the last one is one which is an electric microphone without a polarization voltage. Now let's go back and ask the question, why is it that I have different frequency range? And part of it you can see is also a sensitivity difference between the two. The 40AF has a sensitivity which is 4 times that of the 40AC. Now also what happens is that so what does that mean? So if it means that effectively if I apply 1 Pascal pressure, this will produce only 12.5 millivolts voltage change compared to 50 millivolts here. Now remember how the voltage change happens. It is because of the displacement of the diaphragm. So if the diaphragm displaces more, it will produce more voltage, right? Because the capacitance change will be more. So what it means is that the 40AC deflects less than what the 40AF will do. Now if you go back and simply argue intuitively, when will a diaphragm deflect less? If it is given that, see, remember that the diameter of this diaphragm is kind of fixed. This is the outright diameter with grid is more or less the same, and so therefore it's about 13.2 millimeters. So this is what is called as a this would be about a half an inch. See, we still in acoustics microphone manufacturer still talks about a half-inch microphone, a quarter-inch microphone. So half-inch is basically about 12.5, but with the outside diameter is 13.2 millimeters. So both of these are half-inch diameter. So in which case the basic dimension is the same. So what can change is only the thickness. So the 40 AC is a thicker diaphragm. So as a consequence of that, the sensitivity comes down because it is thicker. So I have, when I apply the same pressure, since it is thicker, it will deflect less compared to a thinner diaphragm, right? Now, what dictates the frequency range? So the lower limit is there is a threshold deflection below which I cannot sense the deflection, right? So for a given pressure acting on that, so how much is the deflection? So you see that that is the lower range. Now the upper range is determined by what is called as, see, the membranes have something called natural frequency. Those who have done a vibration course will recall what is called as a natural frequency. So this natural frequency, the sensitivity remains flat at up to say 60-70% below the natural frequency. So beyond that, the sensitivity starts to change, right? So therefore, when I have a thicker diaphragm, the natural frequency is much higher, and therefore the range of frequencies for which I can use a thicker diaphragm is higher. So here I can go up to 40K. Well, you will ask, well, I think you told in the class, the previous lectures, human hearing is only up to 20,000 hertz. Why am I interested in measuring up to 40 kilohertz? So there may be some applications where you are interested in capturing these things. Certainly, if you want to capture something at 20 kilohertz, you would prefer a 40 AC because its sensitivity is flat beyond that also. Okay, so therefore, as a consequence of this, you can see that the dynamic range 15 dB is again a thinner diaphragm can react better to a small acoustic pressure amplitude. So you can see when I made it thick, I cannot sense anything below 27 dB. So from 15 I have gone to 27 dB. So therefore, if I had a sound at 20 dB, this microphone will not be able to capture that quite well. But the plus of that is the advantage is that I can go to higher noise levels, because 146, if it is above 146, the diaphragm will tear. It cannot take that pressure load. Because it is thicker, it's able to take a higher load there. Now the last one column that is there, the 40 BE, is basically you can see it's a quarter-inch microphone. So depending on the application, you will use either a half-inch or a quarter-inch microphone. Now the thing with a quarter-inch microphone is that I can go to higher levels. You can see up to 168 dB. I can go, and I can also go up to 100 kilohertz. But you see the sensitivity is extremely small. The reason here is that the diameter has shrunk. So the so what you had as a half inch now has shrunk to quarter inch. Therefore, when I apply the same pressure, it deflects even less. So which is why the sensitivity is quite small. So by default, quarter-inch microphones will have much lower sensitivity compared to a half-inch microphone. And this particular model has no polarization, which means it's an electric microphone. Okay. Yeah, so this is what I wanted to say about a spec sheet. So tomorrow, at least you will know the various things that you need to look for when you look for an application. I want to pick a microphone to buy. So some of the things that you need to pay attention to: the frequency range, the dynamic range, and the sensitivity. These are important features that you would look for. All right. So let's okay. The common measuring instrument. So just a microphone is not enough. We need to take that signal voltage change and then convert that into sound pressure values and then put out a number. So in the market you will typically find this device called a sound level meter. What I have shown here is a BNK sound level meter which we have in our acoustics lab in IIT Madras. So this is, you can see that the microphone that we have been talking about sits right there. But then there's a lot of electronics associated with this brick that is there below this. So the sound that is coming there, electrical signal, the voltage coming from the microphone is sent through a preamplifier and then into this circuit that is there, which is there in the brick below. We do what are called as the electrical signal is sent simultaneously to what are called as octave or 1/3 octave band filters. So we'll again see what those octave band or 1/3 octave band filters are. And then the output from all these filters is sent to a rectifier. Rectification, as you know, is turning negative to positive. Then once it goes into the rectifier, you square so that you can get a mean square value and then RMS value, and then you average, you get a RMS value. Normally there are three choices in this sound level meter that you can set. Fast averaging, 125 milliseconds is the averaging time in the RC network. The time constant in the RC network, the resistance capacitance network, is dictated by this averaging time. So when you have a sound which is fairly steady, so a buzzing sound which is fairly steady, then you use a fast averaging as for steady noise, 125. Now if you have sound which is which has some variations, slow variations, so for example the sound is going like so if it has these variations, then 125 milliseconds is not adequate. So we need to go to 1 second, 1000 milliseconds, which is basically 1 second. So that's a slow time averaging. And then the impulse, which is my favorite thing that I did last time, which is clapping. This is impulse sound. So unfortunately neither the fast averaging nor the slow averaging networks are useful for this. So there's a special design for impulse. So you have to tell the sound level meter that what I'm measuring is impulsive noise, and then it uses two types of filters. The high point of the impulse, so you have, when you hit this, you have an increase and then there is a decay. So the upward part of it uses a fast filter, 35 milliseconds. The decay part of it uses a 1500. You saw the profile, it kind of peaks when I clap, and then there is a decay. The decay part of it is done through a 1500 milliseconds RC network, and the upward thing, the build-up of the amplitude, is done through a 35 milliseconds. Okay, of course these numbers are based on some standards that exist. There are, especially for the impulse, there is a lot of controversy in terms of whether these numbers are correct. Alright, anyway, so this is a typical sound level meter. That is this of course a BNK type which we have in the lab. So the filters that are used, which we said it's an octave or a 1/3 octave, these are basically, from electrical engineering terminology, these are what we call as band pass filters. The band pass filters simply means I allow, so if I have a band pass filter, that means there is a lower cutoff and an upper cutoff. So only between those frequencies will the signal energy related to frequencies between the lower cutoff and upper cutoff alone will be allowed. So why do we use band pass filters, octave or 1/3 octave band pass filters? Is because that mirrors our hearing. So this is the way our ear processes sound is in bands. It is not going to do that as a what we call as a narrow band, but it is going to do it in chunks of frequencies. So since we want to mimic ultimately the noise reduction or whatever that you are going to do is with relevance to human hearing, so therefore we want to mirror the measurement process also to come close to the way we do noise processing or sound processing. So the octave band by definition means that octave band, so this bands there's a lower frequency and an upper frequency, but there's also what is called as a center frequency. And when we say octave band, what it means is if the center frequency of the first one is say 100 hertz, one octave higher will be twice this, so therefore it will be 200 hertz, the center frequency, and one octave lower would mean 50 hertz. So so octave simply comes from music. One octave means double the frequency, one octave lower means 1/2 of that. So 2 octaves higher would actually be 2 times 2, which is 4 times 2 square. Right. So there is we have standard center frequencies that are defined by ISO as well as earlier ANSI standards. 63 is, for example, one of the numbers, 63 hertz. Now, one octave higher is 125. Don't ask me why it's not 126, but it is 125, or it is not 62.5, which it should be. But anyway, 63, you have 125, double that, 250, 500, 1000, 2000, 4000, 8000. These are octave bands. Now, the lower cutoff frequency is related to this center frequency by 2 to the power of half. 1 octave is 2. So, I divide this FC by root 2. I get the lower cutoff. I multiply by root 2. I get the upper cutoff. So, you can see FC is basically the square root of FL and FU. Multiply FL and FU. Root of FL FU is FC. What is this? This is the geometric mean. I hope you know this is going back to your high school mathematics. You have arithmetic mean, which is FL plus FU by 2, and you have geometric mean, which is the square root of FU into FL. So, so for example, 1000 hertz, the upper cutoff is 1414, which is 1000 times root 2, and this is 1000 by root 2. So obviously the product of these two is 1000 square. You take the square root, you get 1000, right? So geometric mean, keep that in mind. The center frequency is the geometric mean of the upper and lower cutoff frequencies. So this is the octave band. That is one set of bands that are used. Then you have what are called as 1/3 octave bands. So what this means is that effectively I now introduce two bands in between, and so effectively you have to go through 3 bands to reach 1 octave. So for example, between 63 and 125, you see the red numbers, 80 and 100 are introduced. So I have 63, 80, 100, then 125. The third one basically is 125. Then I have 160, 200, 250, and so on. So between each of these octave band frequencies, now I have these additional bands, and so this becomes a 1/3 octave spectrum. And the lower and upper cutoff frequencies are now related by earlier you had 2 to the power of half. This is now 2 to the power of half to the power of 1 by 3. So therefore it becomes 2 to the power of 1 by 6. So the lower cutoff is the center frequency divided by 2 to the power of 1 by 6. And upper cutoff is basically 2 to the power of 1 by 6 FC. Again, of course, it remains as the geometric mean, but the factor that is used is basically square root of 2 to the power of 1 by 3, 1/3 octave. So for example, 100 hertz, I will have 112.2 as the upper cutoff and 89 as the lower cutoff. So what it means is, if I have a 100 hertz 1/3 octave band filter, any sound which is below 89 and above 112 will be thrown out. So only the energy associated with the signal between 89 and 112, when it comes through that filter, only that will be present in the output. So input may have all frequencies, but it passes through this filter. Output has only 89 and from 89 to 112. All the other things are thrown out by the filter. So you could have so this is typically a hardware that is developed and sits in the brick below the microphone. So it simultaneously passes through this. So when it passes through 100, what comes out is only the energy that is present between 89 to 112. Alright, so that is a 1/3 octave band. Now we come to the weighting scale, right? So I talked about an A weighting scale in the previous lecture. I said I will talk about this, so we have reached that point. The microphone measurements are basically weighted. The reason we do a weighting to the measurement is because we want to mimic human ear characteristics. Now the human ear unfortunately attenuates low frequencies, so we are not very good at processing low frequency. So unless it is very loud, we won't hear the sound. So we attenuate at low frequencies and we amplify at certain frequencies, and so this is to take care of this, it is done through what is called as a weighting scale. So here's a typical A weighting scale. So you can see here the blue curve is basically the A weighting scale. Obviously there's nothing beyond 20 kilohertz. So the human hearing stops here, and it starts at 20, right? So 20 to 200. So the blue line is what is called as the A weighting scale. So you can see that if I look at, say, for example, 100 hertz is roughly about 20 minus 20 gain. So what it means is that if your microphone is saying that the sound pressure level measured is about 80 dB, your ear says it is 60 dB. So it has a gain of minus 20, which means that although the microphone says the sound pressure fluctuations are big enough to put it at 80 dB, the ear attenuates this and says it's only 60 dB. So that means we are insensitive at low frequencies. It has to be really loud for us to perceive the low frequency sound. So again, if I go to about say maybe 200 Hertz, it is around 10 dB. So 80 dB sound at 200 Hertz will appear to be only about 70 dB to the ear. Now at 1000 is where things are equal. So this is zero correction. That means if it is 80 dB as measured by the microphone, the ear will also agree that it is 80 dB. Then there is a small region where it is positive. That means that there is an amplification by the ear. And then after it crosses about 3000, it starts to go down. Alright. But it is not, you can see that it doesn't go down as sharply as it is over here in the low frequency range. You can see all these other scales. We will come back to those scales shortly. Now there's a recent article which is now, when I say recent, it's probably about 3-4 years old, by Per Bruel, who is a very big name in acoustics. I told you about Bruel and Kerr being a big manufacturer of microphones. Bruel along with Kerr were two Danish fellows who started this company that makes wonderful acoustic equipment. So Bruel has been on a lot of committees and so on. He says that the A scale that I showed you over here, the blue line, is an error between 1 kilohertz and 4 kilohertz. So he says that the scale itself is not correct, although that is a standard that is being used. So which is why I tell people, take just because it is there in a standard, you don't have to necessarily be correct. So Bruel here argues that that is not correct. So he suggests the use of D scale. Now why is this? So we'll see what's the difference in between the blue and the this thing. You can see that the D scale, which is the black line, actually has a slightly different weighting at lower frequencies. Like A, it has negative values, but it's not as bad as say at 100 Hertz. A scale says minus 20, but this says it is about minus 8 or 9. And then it kind of goes on, and you can see a big correction is there, almost plus 10 dB, close to about 3 kilohertz, right? So the aircraft people use this D scale, and what has been observed is that they used the A scale and could not correlate the qualitative feel that people had especially in this frequency range. This is because we have our ear canal resonances are in this frequency range. So what happens is, when you have resonance, your pressure is exciting at 3 kilohertz, and because the ear canal has a resonance, I have a higher amplitude exciting at the eardrum, and therefore what is perceived in the brain is much noisier than what the microphone says. And unfortunately the A scale is not able to pick that up, whereas the D scale correction is able to correlate well with what we perceive. So therefore Bruel has been advocating the use of this D scale. Actually the B scale, which is now discontinued in the standard, unfortunately, is more accurate in the low frequency range than the A scale. So you see, of course, it stops at 1000 Hertz. The B scale is essentially for low frequencies, and in fact many people argue that the B scale is, and you can see the D scale and B scale are quite close, especially from about 30 or 40 Hertz onwards they are together. So the D scale is more accurate than the A scale according to researchers in the low frequency region, and of course more accurate in the 1 to 3 kilohertz range also. Alright, so this is from Bruel, so we have to take that. The B scale has been discontinued. The other scale that is shown, which is the C scale, is to be used when the sound level exceeds certain amplitude. So your ear has a certain filtration, a kind of filtering property, attenuation property, which is also amplitude dependent. So your sensitivity depends on what is the noise source level. So when the sound levels are above 100 dB, the ear response is more like the C scale, not like the A scale. So therefore you can't blindly apply the A scale if sound levels are very high. then you will have to use a C scale. You can see that the C scale starts at only around, so if I go to 100, it's almost 0, right? So from here onwards it's almost 0, and then it slightly drops out at the high frequencies. So effectively C scale, if my overall noise levels are very high, then I'll have to use a C scale. Alright. So today in the standards only the A and C remain, and the B scale has been discontinued today. In the old standard, we used to call it as linear or unweighted. What it means is you take the microphone measurements as is without any filter being applied. That used to be called linear or unweighted, but today we call that as Z scale, which is basically from 10 Hertz to 20 kilohertz, whatever the microphone measures, if we report it as it is called as Z scale. So dBA is terminology means which is A weighted. Earlier we simply used to say dB. I am still the old school, so I still say dB, but today people will write dBz, which simply again more or less means dB that I used to write, but it is limited to a range of 10 Hertz to 20 kilohertz. So we have the following things in terms of scales. So these the dBA is often used so that that is when we do a measurement in a factory setting or machinery noise, we always try to report it in the dBA scale, because that comes close to how the human would perceive that sound. Alright, so here is a simple kind of a table telling you applying these kind of sound levels, and also how do we add sound levels. So I have just randomly picked the center frequencies. These need not match with my standard frequencies, so I have arbitrarily picked 100, 200, etc. And I put some arbitrary numbers, 90, 95, 100. These are just random numbers that have been measured, right? So this comes from my sound level meter, and when I apply the correction, the dB gain, so minus 19, so it's 71, about 11 dB, which is 84, 5 dB at 400, 1 dB at 800, 1600 plus 1 dB, 3150 plus 1 dB, and 6300 no correction, so it's back to 0. So you can add. So one thing is band wise. So if I look at that, you can see, if I stare down this, you can see that 400 the linear level, this should be dBz. 100 is the maximum. That means there is something. So if I did this to my whistle signal, so maybe I will do that in the next lecture. If I do this to my whistle signal, so I will possibly stop at this location, even though it is maybe a shorter video, doesn't matter. We will stop at this location. I will come back, and what we'll do is this, of course I have done arbitrarily. So let's say I do this to my maybe the clapping signal, because that tends to have more, we can do for both. So we can do for both the whistle as well as the clapping case. I will break it into these octave bands, and I will use the standard octave bands so that we have no confusion. And then I will calculate the sound levels within those bands, and then tell you basically how this these things come about, right? Alright, so we will stop at this point. This is a convenient location to wrap up this lecture. I will come back. We will do the stack these tables for both the whistle as well as the clapping that we did before. Alright.